So I think I'm going to start with a couple of short comments and then some introductions and then some additional comments. Let me say, first of all, it's, we all know it's kind of the end of the afternoon. We're all kind of tired, and the point of this panel is to be relaxed, interactive, and fun. And when it loses its energy, I'm going to cut it off. If the energy keeps going, we're going to keep going. One kind of comment I want to make about the topic, which is the Venn diagram of signal processing, machine learning, and data science, is if it was data science versus machine learning versus signal processing, and this was a room full of sponsors, and we were all competing for that one bucket of money, this would get very, very territorial and serious, and that's not the point. The topic is serious, but the whole point in this conversation is to have fun, or let's say serious fun. So first, with an introduction of the panelists, I kind of like Rich's comment about me. So I'm introducing myself as the nuisance parameter for the panel. And then I'll leave it to each of the panelists to introduce themselves.
Is this going? Yes. Well, I'm Ron Schaefer, and as you might know, I'm his first graduate student.
Short introduction.
Okay. That's enough.
My name is Victor Zhu. 47 years ago, I came to MIT, and for the last 47 years, I have been very fortunate to have Al as my teacher, my mentor, and not just in education and in research, but in terms of how to be a person and how to deal with life. Thank you, Al.
So I'm Yonina Eldar. I'm also a proud member of DSPG, Al's descendant. Everything you said, I identify with. Besides,
47 years.
Well, not not the 47 years. Thanks for emphasizing that, in case there's any doubts here. I'm also a professor of electrical engineering at the Technion.
Hi, I'm Asu Özdaglar. I'm a professor in the Electrical Engineering Computer Science Department here at MIT. I'm also serving as the interim department head. So I've been also very fortunate to have the chance to work and collaborate with Al. I also want to make the point that I was a student here, graduate student, and Al was the first professor whom I had the pleasure of taking a wonderful course with and getting inspired. So it's a pleasure to be on this panel.
Thanks. Sasha Raklin. I'm in the statistics department at the University of Pennsylvania. I work on mathematical statistics, machine learning, optimization, and Al and I had, over the last year, several fun discussions, so I guess that's why I'm here.
So thanks to all the panelists, and remember, this is all supposed to be fun. And we'll get to a point, by the way, where there's going to be time for any of you to kind of join in on the panel. So what's happened over the last couple of weeks is, I was thinking about the panel, is we've actually exchanged emails among ourselves about the topic of the panel, because it's one of these things where we came up with this idea of, oh yeah, well, let's talk about signal processing, machine learning, data science, and have a really good food fight about it all, not really realizing even what the definitions of these things are. And so then we kind of iterated by email for a while, and it sort of settled into some very, very interesting takeaways. And so I'm going to do something that's sort of unusual with the panel, which is I'm going to Well, I'm going to give you sort of like the trailer. I mean, it's what we think the takeaways are going to be. Now, that doesn't constrain anybody to anything. So there may be things I'm going to say here that came out of our email interactions, and then Junina will say, well, wait a minute, I don't agree with that at all.
I would never say that out. Never.
But kind of what sort of surfaced as we were going through this was, and you heard this with Anantha's talk and other talks, that the boundaries aren't sharp, and a lot of the significant future opportunities actually are in the boundaries. And so there are some problems that you can pretty easily identify as being in the overlap, depending on who's writing a proposal to what sponsor. They'll call the same thing machine learning or signal processing, and that's the game we all play. But there are significant overlaps and problems that we can identify very clearly in the overlaps. I guess another thing that came out was, and I think Anantha made this point, and perhaps Rich made this point, that even with problems that are clearly identifiable as machine learning, the front end is very clearly often identifiable with signal processing. There are also some problems that are fairly easy to define, and we'll look for your help on this later, but problem A, which is very clearly everybody would agree, problem A is a machine learning problem. It's not a signal processing problem. Or problem B, that's clearly a data science problem. That's not a signal processing or machine learning problem. So there are some of those that are easy to identify, a lot that are identifiable as clearly it's just the same thing by a different name, and that a lot of the opportunities lie in the overlap. So to kind of get things going, we're going to head in the direction of defining or trying to define what signal processing is, other than, you know, there are some people I've sort of posed that question to, or with machine learning or whatever, you say to them, so what's machine learning? And the answer is, you know, machine learning. Yeah. Well, those aren't the kind of definitions we're going to be looking for here. I'm going to start by turning to Ron and asking how you would define signal processing, and I think Junina is going to kind of join in on that part of the discussion.
Well, I don't need to say much because Meyer and Petros define signal processing quite well. Basically, it's signals are any pattern of variations that carry information, and processing means extracting that information or transforming it into a more useful form in Petros's terminology. I'm going to leave the question of problems that are clearly signal processing problems and not part of the other structure to Junina. But I'd just like to say that Rich's final comments reminded me of an old story about an old lady who attended a lecture by a professor who was talking about how the earth was round and how it circulated around the sun. And afterward, the old lady said, "Professor, that's wrong. The world sits on the back of a big turtle." And the professor said, well, he didn't want to pick on her. He said, well, what is the turtle standing on? And the answer was, another turtle. And he said, well, what about that one? Well, the old lady says, I'm sorry, but it's turtles all the way down. Now, I'm willing to think after this symposium that our world sits on signal processing, and it's signal processing all the way down.
Okay, well, I don't want to take away from that. That was a perfect ending, so that's hard to beat. But maybe you said serious fun, so that was the fun, and I'll do a little bit of the serious. So, of course, I totally agree with that definition. I think an important part of signal processing, and we actually heard a lot about it in the talks today, and Ron and I chatted about it before, so it was nice to see that that came up in the talks, is the interaction with the physical world. So I think that that's unique to signal processing versus machine learning or data science, where we care a lot also about analyzing the data, but also about how we acquire the data, how we optimize our transmissions, what's the optimal thing to transmit, what's the optimal thing to sense, how do we control the environment, how do we interact with the environment. And these are aspects of signal processing that I think are more particular to signal processing than machine learning or data science. And some of the talks had, I think, really nice examples of intersections of signal processing and biology or signal processing and physics, where that sensing with the environment is important. And I think that also means that as signal processors, when we approach data, we're not just looking at the data, right, as a series of numbers, but we also have to well understand where this data comes from. So understanding the physical phenomena, understanding the biological phenomena. And again, I think that is something that as signal processing people, we pay more attention to than maybe people coming from data science or machine learning. So I think that's part of the fun, right, is that we get to do physics, biology, all these other fields as well, and not just kind of look at the numbers as numbers. That also, I think, touches on what are problems that are more uniquely signal processing. Of course, you could think of many, and there's many in the intersection, but I think problems that have to do more with acquiring data, so sampling or acquisition in general, are more particular to signal processing than machine learning, or problems that have to do with optimizing how we send the data, how we convey information, I think, again, would be, at least in my opinion, viewed more as signal processing, or maybe even information theory, but less machine learning and data science. One more point that I think is very important are bounds or confidence intervals. So machine learning is very good at solving very difficult problems, especially problems that don't have good models, but not so good at saying how well they did, right? Or saying, what are confidence intervals? What are the bounds on performance that we could expect from a certain algorithm? And this is, again, I think, types of problems that are particular to signal processing, really analyzing our performance based on different models, and of course problems that have small data sets, right, which are very much not, I think, machine learning types problems. And again, because we rely on models, we could get away with having small data sets.
And it's going to be interesting eventually to also hear some definitions from the audience. But so now we have a really clear definition of signal processing.
I think so.
And now on to machine learning. So Sasha, how about giving us a definition?
Okay, so it's hard to, of course, define, because it's a somewhat a vague field. But I would say that it's the question that is being studied, and this is a field at the intersection of computer science and statistics and optimization now. The problems studied are how to enable computers learn from experience. And this is, of course, a vague definition, but experience can come from data that you collect if you're about to classify cats versus dogs, or it could come from self-playing, as in AlphaGo, and that's data that comes from experience of self-playing. I would say that, well, first of all, 10 years ago, if I were to say that I am in machine learning, I would always be afraid that people look at me and say, okay, this is an overhyped field. But now it's no longer overhyped. You know, now it's AI and deep learning, so I can feel safe saying that I'm in machine learning. No one would think that I'm overhyping anything. I would say that machine learning is being defined by applications, and the success of machine learning is probably defined by the success of these particular applications, such as text translation, such as image detection, object detection, game playing, such as AlphaGo. There are many other spam detection, right? These are clearly applications that separate machine learning from probably any other field, including statistics. And I think that statistics is an overarching field that should have contained machine learning. The focus of statistics is less on prediction and more on building models, more like in signal processing, I would say. The goal of machine learning is to discriminate mostly. I mean, of course, not exclusively, but much focus is on prediction. So we can talk about why machine learning came to forefront, and it's probably, as Donahoe put in his 50 years of data science, it is partly because of these competitions that there is a quantifiable metric. The whole process is called the common task framework, where you have a data set and you're trying to come up with better and better predictive models for the given data set, and that drove a lot of interest in machine learning and a lot of successes in particular applications. So that's a description maybe of machine learning. I can talk about artificial intelligence perhaps, because machine learning was born out of, I would say, artificial intelligence, of a general goal of creating machines that act intelligently. And in 1950, of course, Turing wrote this paper where the goal was rephrased from can machines think, it was rephrased into can machines do certain tasks as well as humans can do, and that gave rise to pattern recognition, vision tasks, speech tasks, and so forth. I would say that AI took the route of knowledge-based methods and logic, while machine learning took the approach of more of a discrimination or classification questions. And it's interesting that now what is being developed as machine learning is now called AI again, even though AI was typically not not a very successful approach to machine learning problems. We can also talk about data science, but perhaps I can give the...
Well, before you get into data science, so I guess I want to ask, in your view, in the definition of machine learning, does it inherently require large training data sets? Because signal processing is very different in that respect.
Right. When I think of the successful applications, I think of applications that involve quite a bit of data, and that's true. And also these are applications where the model is very difficult to build. If you think about the task of translation or the task of face detection, it could have been that the right way to solve this problem is to actually model the distribution of cats, the model of distribution of the dogs, and then figure out the boundary between them. But I think the insight was to not try to model the distributions, but instead try to model the decision boundary between these points in the high-dimensional space. So I do think that to figure out that boundary, you do need quite a bit of data, but you do not rely necessarily on models that are correct, and so that's a difference between statistics, definitely, and machine learning.
A thought it brings to mind is actually something that Tom and I have gotten into a discussion about, totally unrelated to the topic of this panel. It actually has to do with some very innovative signal processing work that Tom has done, and And he very often refers to it as AI. And so I said to him, well, you mean, yeah, it is AI, algorithm intelligence. And actually, if you think of data science, if you think of machine learning, if you think of signal processing, you can kind of incorporate a lot of those under the term algorithm intelligence.
Yeah,
So-
there's a famous paper by Leo Breiman in 2001 in the statistical science that talks about the two cultures within the statistics. The predictive culture that tries to predict, right? So the goal is prediction, and the modeling culture. And he is musing on the fact that the 90% of the, he estimates, of the statisticians are in the modeling. But if you go out to the industry, what people want to see are, can you form predictions, can you predict well? And so it's more algorithmic, that's true.
I just point out that the large amount of data is required for the design of what is really a signal processing system, input and output.
So, so we've talked a little about signal processing, we've talked a little about machine learning. And when in our interactions over the last couple of weeks by email, one of the questions I had to the panel is, well, who wants to give a definition of data science? And they all pointed at somebody else. Now, actually, fortunately, we have somebody else to point to because of a paper that Petros pointed me to that I know Sasha is very familiar with, and that's a paper by Dave Donahoe. So we can blame it all on him if we don't like the definition of data science that we're about to hear. But do you mind repeating Donahoe's definition?
Yes, I'm not sure that he has a very particular definition, but it's a general field that deals with data, how to process data, how to represent data, how to visualize data. And I know that this sounds very familiar to signal processing people. This is what everyone does. So I don't think there is any crisp definition that maybe even Donahoe would agree on. But he points to the fact that 50 years ago, Tukey was already pointing to mathematical statistics as not the only source of results that should be coming out of statistics, and one should look at data analysis, more of data analysis. How do you look at data, how do you represent it, and so forth. And that should be a big part of the statistics curriculum.
So I actually wrote, oh, sorry, go ahead, Ron.
Well, I'd just like to pose to the panel, is there a difference between signal and data? Are signals a special case of data or what?
So maybe I'd like to say something about that, but I actually wrote down, because I thought you would ask, what
Oh,
Donahoe
good.
says. So I have this piece of paper where, so Donahoe, actually, to be fair, that's not his definition. He quotes this as the way people define data science. Okay,
So he's even pointing fingers.
Right, exactly. So the finger, moves on. But what Donahoe says that other people say is data science is the science of learning from data. It studies the methods involved in the analysis of processing of data. So some of those words, I think, are in fact very similar to the way Ron defined signal processing. But I think a point that's important, and this also goes to the question of, is there a difference between data and signal, is that I think data is part of the signal. So signals convey data. But I think signal processing does other things besides just convey data or analyze data. And this goes back, in my view, to the interaction with the physical layer, right, with the physical world. So there's many other aspects of signals. We may want to recreate signals. We may want to synthesize signals. We may want to acquire signals. We may want to sense or act or control signals. And that's not data in the data science meaning. It's not data that's stored in the computer. So in that sense, I think there's a distinction between data sets are signals, but signals are also the interaction with the physical world around us, which is not typically, I think, what people would consider as data.
So one thing that's going to come up in a short while, not immediately, but Sasha mentioned the relationship of statistics to these fields, and there's another whole field that pervades all of these. At least many of us feel that way, and that's the field of optimization, which Asu is going to talk about. And I think when we get to that point, Asu will put to rest my two folk theorems, which is anything's optimum if you pick the error criterion correctly, and just because it's optimum doesn't mean it's good. And we'll get to optimization shortly, but before we do that, I want to turn to Victor. So Victor, I've known Victor since he came to MIT from Florida, right? And to work in Ken Stevens' group on speech processing. So his roots are very much in signal processing. Victor was the director of the Computer Science and AI lab for many years. He's the world's expert on speech recognition. Speech recognition is what machine learning seems to be very highly focused on these days. So Victor has had roots in all of these fields. And what he has to say about all of this is going to be very interesting. I know where it's going, and it's very interesting. Victor?
Okay, let me just start by saying I have been in many panel discussions, and this is the most orchestrated one by the moderator. And I have more than a dozen messages from the moderator. We all have to submit our first draft and our second draft of what we're going to say. But always, Al said, you don't have to commit to it, okay? So I wrote my first draft, and sure enough, last Saturday, which was the deadline, and the minute the deadline passed, Al sent me a note, say, Victor, are you ready to submit your thing? And I submitted it within the next 5 seconds. I was waiting for that extra email. So many people here are experts in machine learning and in signal processing and data science. And I'm not going to say too much about that. What I'm going to do is to restrict my comments on my personal experience with speech science and technology development as they relates to these three disciplines. I came here to MIT to study speech, science, and technologies because I think, let me be outrageous, I would say speech processing is the hardest problem in signal processing. Okay, I just put it out there. Why is that the reason? It's because we have close to 7 billion people here. We have different linguistic background. We have different socio-linguistic background in terms of dialect and the way we talk about social norms, and we are all different. And to be able to recognize some of the things that, or generate signals of non-human issues is a lot easier. And all the problems that we're facing in speech, it makes it just so much harder. So if you take speech recognition, for example, by the way, Al assigned specific number of minutes that we're supposed to have the opening statement. Nobody followed the rules here.
Of course, rules are to be broken.
Okay, so I can talk for 15 minutes?
As long as you want, Victor.
Okay, anyway, speech recognition, for example, is the problem of converting the speech signal into a set of words or sentences. And in my mind, this typically involves three processes. The representation of the speech signal, which is largely a signal processing issue. The specification of the phonological, lexical, and linguistic knowledge in the form of a set of constraints drawn typically from a large amount of data. And the third issue is to search for the sequence of words that correspond to these, the input signal, and that's largely in the area of machine learning. So speech recognition typically involves three subproblems. The first one is the representation. The second one is to model the constraints. And the third one is how to search for the most optimum set of sequences based on some error criteria. And now everybody should recite what Al said about error criteria and optimality. To solve these problems successfully, one must exploit the symbiotic relationship among the three. In my view, the overlap of these disciplines, plus some other ones, is very important. I think many people don't separate out these three pieces, but they play very important roles. So the idea is that, and that's the idea behind the title of the session, which has to do with the Venn diagram. I think this Venn diagram, as far as speech recognition and synthesis and machine translation is concerned, has very large overlap among these areas. So the first point I would like to make is that these three disciplines, as far as speech processing, speech recognition is concerned, is not autonomous, and it's really intimately related. So, for example, I think it's artificial to make a distinction among these areas, and it would not be appropriate, for example, to model the acoustic signal with a Gaussian distribution if the signal is actually derived from the human auditory system. The peripheral auditory system have much nonlinearities, so you don't want to do that. And the second thing I want to say about this Venn diagram is the fact that interaction among these three components must be guided by a domain-specific knowledge. So the system that you will use for speech recognition will be very different from, let's say, a system for face recognition. But even within speech recognition, a speech recognition for English will be very different from a speech recognition for Chinese because it is a tone language. And even in tone languages, a Chinese tone language where the tones are contoured will be very different from African tone language recognition where the tones are terraced, okay? They don't have a contour. So it is important to make sure that we incorporate or superimpose on this process domain-specific knowledge. Over the last 5 decades, we have seen spectacular advances in speech recognition performance. Today, many of us routinely use speech as a primary means of human-computer interaction with the help of Apple Siri or Amazon Echo and the like. Now, the word error rate is a measure of how good the system is, has dropped from 65% to less than 10%, about 5%. What does that mean? It means 65% means that 2 out of 3 words you have is incorrect, okay? Now it's 1 in 20. Wall Street Journal, the sentence length is typically 22 words. So that means in every sentence on the Wall Street Journal, on the average, you will have 1 error. But it's pretty remarkable. Many people here probably have dictated their email using the Apple Siri system. This is done when the training data increased 1,000-fold from 2 hours to 2,000 hours. This is the amount of data. So it is true, the problem Al posed, that we need a lot of data in order to run the system. But on the other hand, if you go to Brain and Cognitive Science and you talk to Tommy Poggio or talk to Josh Tenenbaum, they will remind us that humans and some machine learning algorithm, like one-shot learning, you can learn by just a few examples, half a dozen examples. So I do think that the amount of data you need depends on the particular machine learning algorithm that you will use, okay? With a few exceptions, modeling and of the constraints and searching for the optimum answers have evolved over the last 4 decades or so from heuristic methods and deterministic methods to probabilistic and optimization-based methods. And today's state-of-the-art system also benefited from 2 factors. One is the large amount of shared data that people can use with a lot of computing power. And they allow us to get much better estimates of the parameters of very complex networks. Formal competitive evaluation also made it easy for people to share experiences and approaches. But I believe the convergence of dominant models and search approaches from heuristic rules, that was when I first came to MIT working in this area, to dynamic programming, to hidden Markov modeling, now to deep neural network. All of these changes could have potential downsides if we don't understand the techniques deeply. I was reminded of something Al told me many years ago when he described the FFT algorithm, and he said, many people probably heard this before too, that automatic transmission enabled a lot of people to drive cars, but it also created a lot of bad drivers, okay? So people just take a routine and start applying it. And at the same time, I think pushing this to an extreme, it can also discourage the exploration of radically different approaches. As a person who is more of a speech scientist and less of a machine learning person or signal processing person than some of the people on the panel, I oftentimes look at the advances made by these new techniques first with envy and then with disgust and then despair. They use so little speech-specific knowledge, and yet they can do so well. So I think it's important for us to have rooms to make use of these kind of things together, again, emphasizing the overlapping Venn diagram. At a symposium celebrating the late Professor Ken Stevens' 60th birthday, John McCool, who is in the audience here from BBN, gave a talk regarding the migration of the field towards what he called ignorance modeling, okay? And what he meant is that our increased reliance on probabilistic approaches to compensate for our knowledge gaps. I subscribe to this kind of what I call knowledge-based but data-driven approach, trying to have the best of both worlds. As our scientific understanding of human speech communication expands, I think we can benefit greatly from being able to exploit this newfound knowledge and achieve state-of-the-art performance with less data and less complexity and less computation. So signal processing approaches, on the other hand, is one of the areas where we haven't seen a lot of attention in the last 3 or 4 decades. By and large, we're still stuck with the male frequency capsular representation and its transformations, something that Al pioneered. A clear exception of the rule is the Amazon Echo. And that machine, instead of trying to polish the doorknob and try to make the algorithm better, what they're trying to do is to make the signal better. So multiple microphones to be able to get the clearest possible signal for the engine to work on. So I think that's a good example, and I remain optimistic that signal processing is an area that's ripe for further innovative growth. And I think we should try to provide an environment to nurture these kind of areas whose real potential has not been realized yet. So my summary is that speech recognition and understanding are prime examples of how signal processing, data science, and machine learning can work symbiotically to solve engineering problems. And some of the most innovative research, in my opinion, happens to be in the area of overlap, and the overlap area is really quite large. To make use of these components effectively, we must remember to make use, wisely, make use of domain-specific knowledge. I think I would just end there.
Thank you very much, Victor. That was really, really profound and interesting. Now, before we get sort of additional comments from the panel and maybe from the audience, there's the whole field of optimization that has become very, very important at MIT and elsewhere, and that in many ways pervades all three of these fields. And I'd like to ask Asu to speak to that.
Thank you very much, Al. So as Al mentioned, I'm going to be focusing on a different intersection. So the interplay between optimization and signal processing and machine learning. My area is optimization theory and algorithms. And even with that, I found myself in the past 10 years or so going more and more to signal processing and machine learning conferences, ICAST or Global SIP or NIPS, interacting with signal processing people, talking to and collaborating with them, advising postdocs in these areas. And this is very much because of, I think, a very natural and fruitful intersection between optimization and signal processing machine learning that happened over the past 2 to 3 decades. And I find this a very, very mutually beneficial intersection in the sense that it's a two-directional exchange. So if you look at convex optimization in particular, advances in convex optimization algorithms, recognition of the modeling richness in convex optimization formulations, and in particular, convex optimization-based relaxations enabled solutions to many problems, I guess, in signal processing that do not have closed form necessarily solutions. So that was, I think, one contribution of optimization to problems in signal processing and communication even more broadly. But on the other hand, many of these problems that emerged from signal processing and communication also, I think, motivated considerations in optimization that shifted the interest and focus of the whole community to a different sort of set of considerations, enabled sort of algorithmic advances as well as theoretical advances. So I'd like to just point out a couple of these intersections. In my homework from Al, I actually mentioned, this is the first time I actually, I agree with Victor, I did homework on the panel, keeping, leaving all my other deadlines. I did my homework, I guess, on time. So I originally mentioned 2 points of intersection to Al, but then like yesterday, thinking about it, I realize I want to point out 3 intersections. So I'll try to do it quickly so that I can get to all of them. So the first one is, I guess, very much, as I mentioned, this sort of the advances in convex optimization and convex optimization formulations and its impact in signal processing, and probably more specifically, sort of convex relaxation-based approaches, the impact of that for solving signal processing problems. And there are many approaches. One prominent one is using these semi-definite programming relaxations for some signal processing problems, many of which take the form of a quadratic program. And Yonina here has worked quite a bit in that area. Applications are vast. I mean, there's so many interesting applications that one can think about. Just a couple of them are things like transmit beamforming, MIMO, ML detection in MIMO communications, sensor network localization, and so on. So there are many problems that take this form. And if you actually formulate these problems as optimization problems, these are hard. You can show nice theorems about their complexity, NP hard, and so on and so forth. So what enabled progress in these areas is very much sort of this, I think this motivated many of the optimization researchers to focus on this so-called STP-based relaxation approaches. And it basically goes through first thinking about a relaxed semi-definite program. This is a convex problem. You can solve it efficiently using numerical means, and then complement it with some rounding or randomization procedure, both of which can be done in polynomial time. And moreover, I think the focus or the interest has been going beyond just computational efficiency to being able to come up with some worst-case approximation guarantees or show in certain cases that these approaches lead to approximately optimal solutions. There are other relaxation approaches. Lagrangian-based relaxation is another one, and sort of people started, I think, figuring out beautiful hidden convexities in these problems, which, you know, to blind eye, you don't really see. For instance, so what I mean by Lagrangian-based relaxation is the original problem is highly non-convex. You consider a Lagrangian relaxation approach to develop a convex dual. There's some duality gap, but still you can reconstruct an approximately optimal primal solution. So one example I would like to give, I was thinking of examples to highlight also in connection to certain applications in signal processing and communication is thinking about spectrum management in multi-user communication systems. So each user basically wants to adjust their transmit power spectral density over a shared spectrum. Our goal is, so we don't want to do orthogonal channelization. How do we think about maximizing overall throughput? So if you formulate this is a, we're designing power spectral density, right? This is an infinite dimensional, non-convex, non-linear, ugly problem that you don't want to touch. But so people basically thought about discretization approaches and then maybe some ad hoc means. And then progress has come, I think, when a couple of optimization researchers have realized that actually, even though this problem is highly non-convex, if you look at the dual, you can show that as the number of tones or discretization goes to infinity, the duality gap vanishes. So you can actually think about approximately and efficiently solving this problem to optimality. So this was one of the intersection points, I think, using convex optimization tools, relaxation approaches to solve difficult problems that don't necessarily have closed form solutions. The other one, which I've sort of seen a lot of interchange, is the need for decentralized processing of data acquired by interconnected nodes. And here, basically, you're thinking about data being obtained, or signals, measurements obtained by a set of interconnected nodes, and you don't want to send all of this data to a single centralized unit to do the processing because of communication cost or privacy constraints. And in the signal processing community, I think this is referred to as the in-network processing of data. And the applications are vast, ranging from decentralized signal parameter estimation, decentralized detection, decentralized adaptive estimation. So when you don't have statistical models of the underlying state, can we actually think about approaches that can deal with unavailability or variation in statistical information, and ideas from stochastic approximation, adaptive LMS-based algorithms, which is something that Sasha works on, becomes relevant. So there's a lot of progress also in this, very much in the signal processing community, in developing decentralized algorithms, efficient, scalable algorithms for processing these. And what I've also realized is this is not just an optimization question. Considerations or constraints coming from networking, signal processing very much dictates the solution that this problem takes. Now, the third intersection is actually both not just signal processing, but with machine learning. You see more and more sort of this area of optimization for machine learning. And that goes basically from the need for processing very large-scale data. So going back to Al's comment, do we need big data? Well, in thinking about finding some learning parametric models, we generally rely on large amount of data. But whenever you say, I have this large data set, even though your problem is convex, all the sophisticated optimization algorithms that have been developed in the 90s completely become impractical. It can't deal with large problem sizes, large dimensionality, large data sets. So that brought another, I think, big change and shift in optimization community in going back to forgetting these sophisticated algorithms, but going back to very simple old optimization algorithms such as gradient descent, first order methods, stochastic gradient descent, coordinate descent, probably one of the oldest methods that have been considered in optimization, and many variants. So a lot of work over the past decade, we have seen sort of new convergence theories, new algorithms with the need to process these large-scale data sets. Now, I feel like, moving forward, we have also a new very active area, which is to understand, all this theory has been done for convex optimization. And the interesting or the puzzling piece is these simple algorithms also seem to be doing very well on these non-convex problems that emerge, for instance, in deep learning or deep neural networks. And our theoretical understanding of why these methods work is very, very limited at this point. So there's been some attempts over the past few years focusing on special cases and saying, okay, the problem has special structure, geometric structure, and so on and so forth. I feel like being able to make progress in this sort of holy grail right now at the intersection of optimization and machine learning goes through very much a fundamental understanding of how we can flexibly develop models with certain properties and couple it with algorithmic development that can actually benefit from those properties. And connection to the physical world and understanding signal generation, information extraction mechanisms will be very crucial, I think, in making that next leap. So,
Thank you, Asu. So let's see, before I invite some comments from the audience, let me ask on the panel, is there anything further that anyone would like to add to the discussion, or rebuttals, or change your viewpoint totally, which is absolutely fine?
So maybe just a quick comment to end with what you said. I think something that emerged from, basically, I think we agree on this because everybody said that, is the issue of models. So signal processing, I think everybody in the audience hopefully would agree with that, is based on modeling, right? Models are crucial to signal processing. Today, less so in machine learning. They're more based on data. And figuring out how we can incorporate models and domain knowledge into machine learning and optimization, I think, is a really useful intersection that maybe is some homework we could all take without a 1-week deadline, but maybe a 5-year deadline to think about how to do that.
Yeah, that's a good point.
Well, I just think back to when I was working in speech processing, and the conventional wisdom was that if we could just model the speech signal better, we could make better speech synthesis, we could do better speech recognition, and so forth. It's turned out that the really good speech synthesis and the speech recognition has become just pasting together segments of speech in the synthesis area. And that's because of some developments that happened outside of that domain, which is in computing. We have tremendous computing resources now, and the question always was, well, what will we do with all of that? Well, now we know the answer, and when we get quantum computing, maybe the emphasis will be in some other area.
So we're getting close to the end of the time, but there is time for some comments from the audience, if anybody has comments they want to make. And it'd be good to have a microphone over there.
So we've heard a couple of times now about the importance of the model, or the Babylonian versus the Greek view. My question is, why do we need the models? If we can design a feedback control system for an autonomous vehicle, say, using machine learning and we end up with a control that works really well with no understanding of the dynamics. Is there something wrong with that?
I have some reactions, but let me, somebody else?
Okay, I can try.
Go ahead, Sasha.
I think if it really works very well 100% of the time, then maybe we don't need to understand. But for that 1% of the time, I think we might want to. So it's not clear, right? There is still value in processing the data in the right way and representing in the right way, and maybe understanding how to model the data, and then maybe the second layer is a classification system that does not need to have a model. But for driving, I think the challenges in terms of planning are much more difficult than planning what to do in a few steps from now, are much more difficult than the task of understanding the space around you and the kind of the obstacles, objects, and so forth.
I mean, there is the question of robustness, and to some extent, it's models that help you understand the robustness. One of the questions I've often asked myself, in fact, I've asked my daughter because she's a commercial airline pilot, if the plane was piloted totally by a deep learning neural net that had been well trained, would you want to fly in it? My answer to that is no. Maybe one or two other comments, if is there anyone else? Mayor?
So I again will discuss this data and models. And actually, there is something that surprises me. I mean, deep neural networks or neural network, I mean, there is a model, right? We have parameters. We fit a model to a data. In all those, what we call data-driven things, there is a model. Maybe the only difference is that we do not assume that the data is generated by this model. The model is for explaining the data, not for saying that this is the true situation. So maybe this is the distinction. I mean, I try to work a lot on this kind of universal thing. You look at the data and you fit model to the data, but with no strong assumptions that the data is really generated by that model. Models should just work. They don't have to be true. And that's my, if you have some comment on that.
Thanks, Mayor.
Yeah, so could I comment on that?
Go ahead, Mary.
So I think with deep networks, you're fitting parameters to the solution, not to the model of the data necessarily.
That's what's important to you, the explanation.
No, but it's not trying to explain the data. It's trying to perform a specific task. And I think that's in some sense really the difference. So you're trying to perform a task, and for the data given, you're optimizing the parameters to form that task, which is usually a simple task or a binary task. Whereas
It's really great to watch an Israeli energetic discussion.
no, if we change to Hebrew, then it will be interesting. So we're both still being polite, but right. So you're trying to fit the parameter. I'll put my hands down so that I'll not be interpreted as aggressive. So you're now I lost my line of thought. So yeah, you're fitting parameters to solve a specific task. Yeah. Whereas if you're thinking about, and I totally agree with you, you could use machine learning algorithms to learn the model, then take that model and solve a signal processing problem. But I don't believe that's what machine learning methods are doing today.
Yeah,
So I can comment, just answer that? Israelis,
Then
right?
I have to answer back.
A quick answer. The classical example of the LMS algorithm, Widrow's, or a linear equalizer, that's what I said. I mean, you fit a model, you explain, you build an equalizer which is linear. You don't assume that it's the best thing. When you do noise cancellation, you don't assume that you just constrain your solution to be a linear algorithm and you train it. So that's what we did in signal processing, and we called it model at that time or whatever, and it worked. And now machine learning are just doing it in a much larger scale. but that's what they do. They fit model to the data.
Not to the data, to the solution.
To whatever,
You just
to
said you're
whatever you want to
constraining the
do.
solution. Okay, we'll take it offline. But
So I'm going to let that discussion continue.
Al invited this in advance, so could we tell everyone that this was planned?
Thanks.
And Gene is sitting right next to him as the court jester, so he's encouraging it. This is.
Oh, yeah, Gene, the court jester, right.
I think Sid had a question over here too.
So I think at this point,
I think there's one more question from Sid.
Yeah, go ahead.
One of the aspects of data science, for me anyway, is that you look for structure in data. And you don't talk so much about the models as you do the structure. Now, very often that can be stated in terms of a model, but the fact that we teach courses in signals and systems, that the system is the processor. If the system, in fact, is more than a representation, but is actually an algorithm or a piece of hardware or something of that sort, then when you're doing optimization, you're doing parameter identification, you're actually finding parameters that you're going to use for some purpose. If it's a representation, then it may end up doing precisely the same thing, but you're doing it with a different sort of motivation or argument. So the old signals and systems dichotomy, I think, is very useful in some cases, and in other cases it's not. And so in a certain sense, everybody's comments have been true in certain arenas. And the question is which of them work in the arena that you're trying to develop?
So I look forward to this kind of conversation and discussion going on well beyond today. I'm sure it will go on well beyond today. So I'm going to call a close to the panel and thank all the panelists for joining in. Thank you very much. And before I hand the microphone, well, Tom has a microphone. Before I virtually hand the microphone back to Tom, I just want to make a couple of quick final comments. I really want to thank the organizing committee for this whole event and for all of you participating in this symposium. I really feel honored by it. I really do. I mean, it's just very touching, and all of the really wonderful and warm comments that were made. The thought I'd like to leave this with is that this symposium really honors the past and particularly the future of signal processing. Signal processing has a really, really rich future, actually much richer than the past, because there are lots of other opportunities to bring into the field. And so the future of signal processing really is just beginning, and that's really the way I see it. So thank you all for all of you for coming and sharing this with me, and thank you for the honor of doing it in my honor. Thank you. Thank you.
Thank you, Al. So there are just a few additional people. Oh, there are just a few additional people that I'd like to thank very quickly before we all go, since we've reached the end of the day. So first of all, the EECS department, thank you so much for your support of this. Bill Tilden and Ann Stewart, you guys have been absolutely amazing. I think one of the things that I wanted to mention, I'll close maybe with another quote of Al's that I really like, that I think describes perhaps today, although I don't think it initially described today, which is, I think probably this quote this probably pertained to you more in the 1960s, 1970s, 1980s to today, but I think it also pertains to the future, which is that you're always exactly in the right place at the right time. It's just a matter of recognizing that you are. So I think that today, if you take a look at some of the talks that you've seen, hopefully they'll spark ideas and we'll all be able to recognize that we are exactly in the right place and at the right time to define the future of signal processing. Another thing I'd like to mention, as I've been walking around talking to people, I think I've just heard so many warm stories about Al, over the years, and I think it's been really just awesome to hear these stories, and I'd like to, I guess, if I were to say what the common theme among many of these stories is it's a sense of gratitude that a lot of people feel. Al, you've touched so many lives. I know that it's, you're not someone who likes to be put in the spotlight and have these kinds of, things said, but it's worth saying. And I also wanted to say thank you from myself, for taking a chance on me as a student, for taking you under my wing academically, and for also being a wonderful mentor and personal friend. And so I think, this concludes the program. I think from everyone here, I think we can all say that we continue to wish you the best, and thank you.